Hi everyone, welcome back. We're going to pick up this week with the rest of our wetland unit. This is part 3 of the lecture series. Our learning objective for part 3 is to calculate wetland storage volumes and to explain the hydrologic function of wetlands in the watershed. By increasing the storage of water in the watershed, wetlands can impact a few of the flux terms in the water cycle, including both high and low stream flow, percolation and groundwater recharge, and evaporation. This illustration provides a classic example of how increasing surface water storage in a watershed, in the form of lakes and wetlands, can influence hydrograph shape. These 3 hydrographs were all observed in the Torne River Basin in northern Sweden, shown here. The annual hydrograph is dominated by the cycle of snow accumulation and melt, so you can see there is no stream flow in the winter, but then it rises dramatically in May. The red line represents the watershed that has the most lakes and wetlands. You can see that relative to the black line, there's a greater lag time, this time period, a lower peak flow here versus up here, and greater base flow throughout the summer months, this line versus this line. Overall, the impact of increased wetland storage is the attenuation of stream flow response to rain and snow melt events and increased evaporation of the stored water. This can also lead to localized cooling of air temperatures, since this evaporation consumes energy. So let's think about the water budget of a wetland environment. The exposed wetland area can receive direct precipitation, and it will lose water to the atmosphere via evaporation. Water can flow into the wetland from the surrounding landscape, either as surface flow, stream flow, or groundwater flow. This water will increase the water level in the wetland, shown here in teal. This increases the surface area. At the same time, increased storage can increase the outflow rate, but the flow rate out of the wetland will tend to be later and smaller than the flow rate into the wetland. Overall, the change in storage in the wetland environment versus time is equal to the difference between the inflows and the outflows. In order to quantify the influence of storage, we need to quantify the amount of storage in the wetland. For specific sites, we can do this using the area depth relationship. This is a graph or table describing the flooded area of the wetland, shown here on the x-axis, as a function of the water depth in the wetland, shown here on the vertical axis. As the water gets deeper, it expands out to cover a greater land area. This relationship can be integrated to find the volume of water stored at any point in time and the remaining storage capacity. For example, in this illustration, let's assume the water in the wetland is currently at a depth of Z2. The current surface area is then shown by A2. The wetland can continue to collect water until the water level rises to Z5, at which point the capacity will be filled and the wetland will start to act as a source for saturation excess overland flow. The storage capacity remaining in the wetland is the shaded space between Z2 and Z5. We calculate this volume by summing the storage in each layer. So for the incremental volume of the layer between Z3 and Z2, shown here, the storage is the average of the area of this layer, A2 plus A3 divided by 2, times the thickness of this layer, Z3 minus Z2. Similarly, the volume of storage in this orange layer is the average of areas A3 times the thickness, and the volume of this yellow layer is the average of A4 and A5 times the thickness. You then sum all 3 of these to find the total storage volume remaining in the wetland. Please note that it is necessary to calculate the storage of each layer separately and sum. If you try to average all of the areas and multiply by the overall change in depth, you will not get the same answer. This example demonstrated the storage capacity remaining in the wetland. If you want to know the current volume of water stored, you would perform the calculation for the first two layers in blue, as shown here. Now we're going to think about the temporary increase in storage in a wetland from the perspective of the runoff flowing into the wetland. We know that water flowing into a wetland increases the water level, increasing storage. The maximum increase in storage is of course equal to the volume of water in the inflow hydrograph. Since the hydrograph is a graph of discharge rate in volume per time versus time, to get the total volume, we need the area under the curve. That's what's shown here, shaded in blue. This is applied calculus for those of you who like to insist that you will never have the need for calculus in any other class. To calculate the hydrograph volume, we will use the same trapezoidal rule that we use to calculate wetland storage volume. So if you want to know the volume of streamflow that entered a wetland between time 5 and time 6, we multiply the average discharge rate for that interval, shown here, D5 plus D6 divided by 2, by the elapsed time, T6 minus T5. The only thing to watch out for is whether the time units are the same between discharge and the time axis. So if your discharge is in cubic feet per day, and the values are given once per day, you're fine, right? Cubic feet per day times day. But if discharge is given in cubic feet per second, you will need to multiply it by the number of seconds per day in order to make the time units cancel. Let's do a larger example. The graph to the right shows the inflow hydrograph into a local wetland in blue. We want to know the total volume of water that entered the wetland during this event. The time step is hourly, and the discharge is given in cubic feet per hour. We know that our equation is going to be the summation of the average discharge in each interval times the amount of time between the intervals. So for our solution, looking at the volume that entered the wetland between hours 1 and 2, we have the average of 2 cubic feet per hour plus 0 cubic feet per hour times 1 hour. So it was 1 cubic feet of discharge. This was a 10-hour event, so we have 9 distinct calculations to make. Once again, you cannot simplify this by multiplying the average discharge value by 9 hours. It's not the same answer. So our total answer is going to be the summation of all of these individual calculations, or 48 cubic feet. I said previously that the volume of the inflow hydrograph represents the maximum increase in storage in the wetland, because the water can start flowing out of the wetland almost as soon as it starts entering, and this outflow will work to decrease the storage in the wetland. We know that the storage volume in the wetland is increasing, dSdt is greater than 0, when the inflow hydrograph is above the outflow hydrograph. So, in this region. In contrast, the water level in the wetland is declining during the period when the outflow hydrograph is above the inflow hydrograph. Shown here. I should have said that the dashed line represents the outflow hydrograph. The difference between these hydrographs is the volume of water that goes into temporary storage. So during the rising limb, this difference between the hydrographs represents water that's going into storage in the wetland environment. We can use this information to come up with a theoretical estimate of the potential for peak flow reduction based on the available storage capacity in a wetland. In this equation, the ratio of the outlet peak flow rate, QPO, to the inlet peak flow rate, QPI, is equal to 1 minus the ratio of the current storage capacity in the wetland to the total volume of the inflow hydrograph. This applies for values of V greater than S. If there's enough space in the wetland for the entire inflow hydrograph, there may not be an outflow hydrograph. It also implies that if the available storage capacity S is small, because the wetland is already full of water, then the peak flow reduction will be small. Once again, V is the runoff volume, S is the temporary storage volume, QPO is the peak outflow rate, and QPI is the peak inflow rate. Let's finish our earlier example to find the theoretical peak flow rate reduction for this scenario. In this case, we are given the outflow hydrograph, shown in orange, so we don't really need to estimate the peak flow rate. We are doing this for illustration purposes. So we know that the outflow rate equals the inflow peak times 1 minus the ratio of storage to inflow volume. We know from our previous calculation that the inflow volume is 48 cubic feet. And we are given in the problem that the temporary storage capacity is 16 cubic feet, and the inflow peak is 15 cubic feet per hour. So our solution, the ratio of the outflow peak to the inflow peak, is 1 minus 16 over 48, or 2/3. This means that the outflow peak is 2/3 times 15, or 10 cubic feet per hour. So in summary, the downstream hydrologic effects of having wetland storage in a watershed is flood control. By taking runoff into temporary storage, wetlands can delay the peak flow timing, which helps to decrease the peak flow rate. By storing water on the landscape, this increases the time available for groundwater recharge to occur. In addition, the water available at the surface is also available for evaporation throughout the growing season. So there tends to be a greater rate of evaporative loss in wetland-dominated watersheds as well. This concludes part 3 of our wetland unit. You can now move on to lecture 4.